Just as a linear force can cause an acceleration on an object, a torque can cause an angular acceleration on an object. So just to show you this, let's consider the case where we have, let's say, a particle tied to a string that's moving in a circle. So I'm just going to show you the top portion of the path of the particle, and let's just say it's going down to the middle of the circle. So if this is the case where the particle is on the string, we know we have a tensional force that is inwards towards the center of the circle. If this were a case, and we're going to pretend that this is a case where the particle is not moving in uniform circular motion. If it were moving in uniform circular motion, then we would have not a change in the magnitude of the speed, we would just have a change in the direction. But in this case, let's pretend that we have the particle that's accelerating. Well, that tensional force inward would cause the change in the direction, but we'd also have to have a force tangent to the circle. So I'm just going to call this F sub t just for a tangential force, which would cause a change in the magnitude. And because we have a tangential force that is causing a change in the magnitude of the speed, according to Newton's second law, that tangential force is equal to the mass times the tangential acceleration. So just to rewrite this, I'm going to rewrite this as the tangential acceleration equals the tangential force divided by the mass. Now, we also know that there is a relationship between our tangential acceleration and our angular acceleration. Since we know that the tangential acceleration times the radius of something that is moving in a circular path is equal to our angular acceleration, I'm just going to substitute in. So I know that, I'll use a different color here just to make this a little bit easier. I know that not the tangential acceleration, but the angular acceleration times r is equal to that tangential acceleration. So if I just simplify what I have here, this is what I get. So if I wanted to solve for the angular acceleration, I would have the angular acceleration equals that tangential force divided by the mass times the radius. Just to keep going from here then, I also know that the torque that I have is equal to the distance from the axis of rotation times the force that's being applied that causes that rotation. So if I relate these two equations, the angular acceleration that I have, let me just move that back, the angular acceleration and the torque, I'm just going to substitute. I can say that the force is equal to the torque divided by r. So if I substitute that into our other equation here, I have the angular acceleration equals the torque divided by r divided by m times r. So if I simplify, I have the angular acceleration equals the torque divided by mr squared. So what that means is that there is a relationship here between the torque and the angular acceleration, but it's not just a simple F equals ma equation. It's the torque divided by m times r squared that equals that angled acceleration. What's important to understand is that the angular acceleration, just like the torque, is dependent on the distance that you have from the axis of rotation, because that's what that r is. So the r is that distance from the axis of rotation. So when you have different rotation points, you're going to have different angular accelerations depending on that axis of rotation. So it's important to make clear what that axis of rotation is. Now, if we pretend that we have a rigid body, so instead of just a single particle, let's just say we have some sort of a rigid body. So we have a particle here, we have a particle here, we have a particle here, and let's just say that x is the center of our axis of rotation. So what's going to happen now is if I were to apply a force, let's just say we have a force F1 on this point, let's say we have a force F2 on this point, let's say we have a force F3 on this point. What's going to happen is the combination of all of these torques will will give us what happens with the rotation of this rigid body. But it's also important to understand that all three of these have the respective distances from the center. So if I call this R1, if I call this R2, if I call this R3, what's going to happen is each one of these torques, so torque 1 is equal to the mass of that first particle times the distance that first particle is from the axis of rotation squared times alpha. The second torque is m2 r2 squared times alpha. And the third torque is m3 r3 squared times alpha. So what happens now is if I wanted to find my net torque, if I just added these up, what I'm going to get is net torque is T1 plus T2 plus T3, which equals m1 r1 squared times alpha plus m2 r2 squared times alpha plus m3 r3 squared times alpha. And if I just factor out an alpha, what I'm going to end up with is the sum of all these m1 r1 squareds, or mr squareds I should say. So m1 r1 squared plus m2 r2 squared plus m3 r3 squared. So what happens is when we sum all of these up, we get this quantity here, which ends up being a constant. And this constant that we have is what we call the moment of inertia. And we're going to define that as the variable I. So typically what you're going to have given to you is the moment of inertia, and then you're just going to have to find the angular acceleration if you're given the torque as well, or if you're given the angular acceleration, you can find the torque. But that moment of inertia I is kind of like the mass. It's like the mass quantity of something that is undergoing rotation. So in general, what we're going to do is we're going to write this down as the acceleration, the angular acceleration of an object is equal to the net torque divided by the moment of inertia. So instead of just mr squared for an individual particle, if we were to sum all of those up, like what we did down here on the bottom, we would get the moment of inertia of this rigid body, and the moment of inertia of the rigid body is going to be I. So we use that in the equation. There are different ways to calculate the moments of inertia. We're not going to worry in this course about how to calculate the moment of inertia. It's going to be a quantity that will be given to you, so you should be able to find the torque or the angular acceleration from the moment of inertia that is given to you.